I'm very happy to be here. When I was a young professor, Donald Peterson, whom the award before the break was given, was a force of nature at Berkeley. His idea was if we're going to build software in universities, we should give it away for free, including the source. So kind of started the open source movement. The rest of us followed. And I remember being told before I gave my first talk here that this is the world's best organized conference, and it still is 40 years later. So I have 3 parts to my talk. I'm going to tell you about, first, for you circuit designers who may not have been keeping up on computer architecture, I'm going to do 50 years in 15 minutes to set the foundation for 2 exciting new trends of domain-specific architectures and open architectures. So, in the 1960s, IBM had this big problem. They had 4 different incompatible lines of computers. They had their own instruction sets, they had their own software stack, they had their own operating systems, they had their own market niches. So the engineers at IBM made this bet that they could invent a single instruction set that would handle all the markets. Basically, they invented what would be called today binary compatibility. The same program would run on the 8-bit version of the 64-bit version, and all the software would be the same. Now, that was a bold thing to try, and then, as is now, the hardest part of processor design isn't the data path, isn't the number crunching part, it's the brain of it, it's the control. So how are they going to pull all those things together? Maurice Wilkes, one of the computing pioneers, had written some papers as an academic that he thought there was a better way to design control. Since at that time, logic was slower than ROM or RAM, and ROM was faster and cheaper than RAM, his idea was to specify control as a matrix. And he referred to every word of that ROM as a micro instruction, so it's more like programming. So IBM decided to make that bet when they bet the company that they could pull it off. And in 1964, IBM announced the IBM 360, the biggest announcement in the history of the company. And you can see on the left there were 8-bit computers, on the right there were 64-bit computers, and they all ran the same instruction set. The microcode varied. Basically, the more powerful the hardware, the wider the microinstruction must be. In this case, the fastest ones was 3K by 87 bits. And that the narrower one would be simpler hardware and less ROM. It would be 50 bits wide, but it took more instructions since it was a little bit slower to get there. And IBM won that bet. That instruction set, classic, is here 50 years later. There's a descendants of it still for sale today, and they still dominate the mainframe market. So what happened next is we moved to the mini-computer industry and semiconductors. Logic, RAM, and ROM are all built from the same transistors, so the RAM and ROM are about the same speed, but with Moore's law, you could have a lot bigger control store, so microcodes got bigger. So what this meant was you could build a bigger instruction set interpreter, which meant you could have more complicated instruction sets. And a classic example of this is the VAX mini-computer from Digital Equipment Corporation, and it had 5,000 microinstructions, each 96 bits wide. Now, in the semiconductor industry down here in California, Gordon Moore, who was leading Intel, believed that the instruction set that they had, the 8080, the next one they did, they'd be stuck with for the whole life of the company, just like IBM is with the 360. So he wanted to make it a really great instruction set, so he hired lots of PhDs in computer science, sent them to Oregon to invent the next great instruction set. And eventually they came back with an incredibly ambitious one. It's 32-bit addressing, where they needed 16-bit addressing, and it was what's called a capability-based operating system today. The instructions weren't multiples of bytes, they were multiples of bits. They could be 2 bits wide or 19 bits wide. A lot of microcode, and they even wrote their own custom operating system in an esoteric programming language. Alas, and of course, when it was released to tremendous fanfare, the greatest thing since electromechanical analog computers. Alas, the problem was it had big performance problems, and actually the microprocessor didn't fit in one chip, and usability, and so it didn't turn out as well as they hoped. And in fact, they warned Gordon Moore several years into it that they weren't going to make the deadline. So Moore was forced to start an emergency project that he tagged a small group of Intel engineers and gave them 52 weeks to design an instruction set and to build a microprocessor and get it to the market. So that gave them only 3 weeks of elapsed time to design the instruction set, about 10 weeks altogether. So in the time, they kind of took the old instruction set, widened it to 16 bits, added a few things so you could be assembly language compatible. And the 8086 was announced, but it wasn't that exciting a product and there wasn't tremendous fanfare. Fortunately for Intel, at the same time, IBM had decided to enter the personal computer market following Apple. And they really liked the Motorola 68000 instruction set since it was like the IBM instruction set, but it was late. So they ended up picking an 8-bit bus version of the 8086. And they thought they'd sell 250,000, but they were wrong. They sold 100 million personal computers, and that made the 8086 family an overnight success. And binary compatibility with PC software meant this was an incredibly valuable franchise. But what happened to these microcoded machines? This is a picture of John Koch, one of the heroes of computing. And he and a group at IBM Research were building something that didn't need microcode, and they had built a nice compiler for it. They said, well, what would happen if we tried that on basically the IBM 360 instruction set? Suppose we just used the simple instructions that didn't use the complicated ones. Well, programs ran quite a bit faster, 3 times faster. And then over at Digital Equipment Corporation in Boston, some engineers took a look at the microcode to see how it was used and found that 20% of instructions were 60% of the microcode, but it was almost never used. So it wasn't clear that that was necessary. So that led to the reduced instruction set ideas. So instead of having RAM memory with a microcode interpreter in that, instead we would replace that with an instruction cache, and they hold the instructions of the program, and you can just compile and change what's in that RAM. And you'd use really simple instructions. You can think of them as simple as micro instructions, just not as wide. And that made them easier to pipeline them to get even better performance. And then with Moore's Law, we were able to get that 32-bit data path all into a single chip with no chip crossings, and it was a very attractive design. But the problem was, in those early days of RISC, was trying to explain why it's a good idea. So this formula was the key to explaining it. So the time per program, how long it takes to run, could be broken into these 3 factors. The number of instructions you execute per program, the average number of clock cycles per instruction, and then multiplied by the time per clock cycle. Well, people noticed that the RISC architectures with simple instructions, you have to execute more of them, so that seems like a bad idea. But DEC engineers, to their credit, a few years later published what the actual facts were, and that the CISC instruction did, in fact, execute fewer instructions, maybe half as many, but the average number of clock cycles per instruction was about a factor of 6 bigger, so RISC was about a factor of 3 faster, so RISC architectures took off. Intel cleverly had the hardware resources. That they decided to do was translate the old CISC instructions of the x86 internally into RISC instructions, and then anything that the RISC guys came up with, they could include in their microprocessor as well. So this was very successful, and IBM grew the market to 350 million x86 microprocessors per year. And eventually, that technology and that instruction set dominated the market and took over the servers as well as laptops. So that's the PC era. What happened in the post-PC era? Let's say that started with the introduction of the iPhone in 2007. Well, now instead of buying a microprocessor from a company like Intel, it's IP that goes onto an SoC, which means you value not just performance, but the size and energy is incredibly valuable. So what's happened in this post-PC era is now there's more than 20 billion microprocessors every year, and but the x86 hasn't penetrated most of that market. It peaked in about 2011. It's been declining about 8% a year ever since. In fact, they sold fewer of them a couple years ago than they did in 2007. x86 servers are dominating the cloud, but the cloud's not that big in terms of the number of chips. The chips are expensive, but not that many. Maybe there's 10 million servers in the cloud today, which takes almost no time. So today, 99% of the processors made in the world are RISC processors. So RISC won that era. The next idea in architecture that came along was very long instructions words, or VLIW. That was supposed to replace RISC and CISC. And the idea is, This longer instruction could specify lots of operations at the same time, and you could put a very powerful data path with lots of ALUs in it. Then how are you going to control it? Well, the hardware was really simple. Some things would take 1 clock cycle, some things would take 3 or 4. The job, it was up to the programmer, or importantly, the compiler, to fill in the slots to make it all work right. If you didn't put the right distance between them, you wouldn't get the right answer. There was no hardware interlocks that you'd see from pipeline. So that was the idea of very long instruction words. You shifted all the work to the compiler, and the advocates said compilers are ready for this. They can handle that complexity and schedule things appropriately, and it's all going to work. Around this same time that VLIW was getting a lot of notoriety, Intel had to make a business decision. They had successfully taken the 886 from 16 bits to 32 bits with the 8386. They just made the registers wider. They could do that again for the 64-bit thing because programs were getting better than a 32-bit address space. However, AMD had the rights to also make x86 processors. It wasn't a great thing for business. And, you know, the architecture itself was that thing that was designed in 3 weeks, so it wasn't the greatest architecture. So they decided to embrace VLIW. In fact, they decided to do that in conjunction with Hewlett-Packard. They called it EPIC, for explicitly parallel instruction computing. It was basically a binary compatible version of a VLIW. And we had these 2 big companies pushing it. The name of what Intel calls it was IA64, the other one was IA32. So the 64-bit version was this VLIW, and AMD was squeezed out. Now, AMD had no choice, but because it was squeezed out, had to make a 64-bit version of x86. It took a while for them to get the first chip. It was several years late, but they built several more. And a bunch of companies at the time, given it was these powerhouses, HP and Intel, saying this is the future, they just gave up on their RISC processors and pledged to use Itanium because of the power of the companies and the arguments that were being made. So what happens in computer architecture is we make these arguments that maybe you'd have in a bar here at ISSCC, and then we spend billions of dollars to see who's right. So what happened? What happened is the VLIW was an epic failure, was what happened. The problem was unpredictable branches was hard to schedule in software. When you had a cache miss, it was hard to figure out how to schedule that thing. And the final one was, it's called very long instruction words, so the programs got a lot bigger, and that's a problem when you have million-line programs. And so as Donald Knuth, the famous computer scientist from Stanford, said, the Itanium approach was supposed to be fantastic, but no one could build the compilers. Because it had gotten so much notoriety, it became something of it was ridiculed by the chip industry, and somebody changed the name from Itanium to the Itanic, inspired by the infamous Titanic ship. So it didn't work. What happened was Intel was forced to follow AMD's lead and just extend the instruction set. So finishing up part 1, what's the consensus on instruction sets today? It's not CISC. No one's introduced one in 30 years. For general purpose things, it's not VLIW. Nobody's tried that in 15 years. The good news for VLIW advocates is it works pretty well in digital signal processing because the programs are small, the branches are easy, and it doesn't have caches. They have software-controlled memory. So it found a home, but not for general purpose. So what's left? RISC. 35 years later, to my shock, RISC is still the best ideas going forward for instruction set design. Okay, let's go to part 2, domain-specific architectures. So, end of Dennard scaling, end of Moore's law that we talk about a lot here. Those are big things. Architectural limits, binary compatibility below the covers, we would have out-of-order execution ideas, but those kind of ran out of steam about 15 years ago. And so we went to multi-core because we couldn't build better unicores. We needed a power budget, but we were limited by how many cores you can usefully put together, like 8 or so for a lot of applications. Gene Amdahl, a famous computer architect, said in Amdahl's law that if 1/8 of the time it's sequential, no matter how, if you even have 1,000 processors, the maximum speed up is a factor of 8. So that's kind of limits the benefit there. So we've got to do something new. And in fact, you can see this reflected in the first picture, the first figure in our textbook of Hennessy's and mine on computer architecture. The good old days, we had the CISC architecture was with only doubling performance every 3.5 years. And then we had this RISC era where it was doubling every 18 months, and you couldn't wait to get the next laptop because it was so much faster than the one you had. That's what many people thought of as Moore's Law, is that speed up. With the end of Dennard scaling and power budgets, we had to switch to multi-core, so you could see it slowed down to about doubling every 3.5 years, and then with Amdahl's law about the benefits of multi-core limiting, it slowed down to every 6 years. And I was shocked in the latest edition of the book is the Intel servers and standard benchmarks are only like 3% faster per year, doubling every 20 years. So we've come to kind of a grinding halt. So what are we going to do? Transistors aren't much better, power budget's limited, we've already done the multi-core trick. Only thing left that architects know what to do is what we call domain-specific architectures. We're going to design for a narrow class of things that won't have to do everything well, but what it does well, it will do very well. So an example of a domain-specific architecture happened at Google. Google about 5 years ago thought with neural networking they were going to be able to do things like speech translation, and calculated that if they didn't do anything to accelerate that and use standard CPUs, Google would have to double their cloud, double their data centers to handle the load, which would be extraordinarily expensive. So they started an emergency project to build a custom hardware chip to do the inference part of neural networking. So what's on that chip is, the heart of that chip is the matrix multiply unit. That is 65,000 8-bit multiply accumulate units, which is kind of an amazing number. At a 700 megahertz clock rate, that's more than 90 trillion operations per second. And in terms of the max, like 25 to 100 what other chips have. It's got 4 megabytes of memory to handle the results, and another large memory that's a buffer to handle other operations at 24 megabytes on the chip. The so-called parameters or weights that you need for neural networking don't fit on the chip, so they have to be brought in from a DRAM over a DDR3 interface. Here's the floor plan of the chip, and that matrix unit is the yellow one on the right. That's a quarter of the chip. The unified buffer and the accumulators are very large memory. That's about another 40% of the chip. So 2/3 of the chip are those two things. In architecture, it's hard to compare absolute scale, so you compare it to other things. The contemporary chips of the time were a CPU and a GPU. And if you look at the leftmost column, the TPU is only about half the size of those other chips, and it's also about half the power of those chips. What about performance? So to explain the performance, it's not just peak performance, it's the actual performance of delivered things. A useful graph to show that is called the roofline model. So the roofline of the chip has a flat part and this diagonal part. So the flat part of the chip is kind of the speed of light. For the TPU, you can't do faster than 92 teraops per second. It's physically the speed it will go. Now the slanted part is when you're limited by the memory system, and typically you're either limited by computation, limited by the memory system. And then what the graph uses to decide where your program is running is the average number of operations per memory byte fetched. So if you have a lot of operations per memory byte, you're over there on the right-hand side where your computation limited. If it's few operations per memory byte, you're in the slanted part, memory limited. So what does a TPU look like? A TPU looks like a really long slanted roof because it didn't have that great a memory system, it had huge computation. And you can see 4 of the 6 neural networking apps are memory limited, but they're pretty close to the roof line, so they're operating pretty efficiently. Here's the CPU. You know, it's got a lower roof line, but you know, the apps are closer to the top, but the GPU is the apps are quite a bit below it. So why is that? So one of the surprises in analyzing the results that we didn't know in advance was that response time, 99th percentile response time, was vital for these user-facing neural networking applications. And as you can see between the green and the red on these figures, for the CPU and GPU, the 99th percentile 7 milliseconds response time is far off the peak of what these things could do if you didn't care about the response time. Whereas the TPU from Google is pretty close. There's a small difference there. So that's one of the advantages, or one of the requirements that the TPU worked out. If we put all of them together, you can see on a log-log scale what the relative looks like, but I don't think log-log scale, I have to think linear, so that's what it looks like. So it's a lot faster. So how much faster is it? If we compare our 6 benchmarks, the GPU is about twice as fast as the CPU. The TPU is about 30 times faster than CPU, so the TPU is about 15 times faster. Now, in a data center, which is where the TPU is placed, you don't just care about performance, you care about total cost of ownership, which is the cost of the chip as well as the operating for the electricity and things like that. Companies don't reveal their total cost of ownership, but it is related to the performance per watt, which we can talk about. So this slide shows the performance per watt 2 different ways. Since it's an accelerator that goes into an Intel server, you can either include the host power or not. But if we don't include the host power, it's a factor of 80 in the performance per watt over the CPU and a factor of 30 over the GPU. Now remember I said it was an emergency project and they just used standard DDR3 interfaces, whereas the GPU has the graphics GDDR5 interfaces, which is much faster. So a natural question is, suppose we'd had the time to be able to use the GDDR5 memory instead, what would have happened to the results? And it would be kind of astronomical. The TPU would have been a factor of 200 times the performance per watt of the CPU and a factor of 70 times the performance per watt of the GPU. All right, summarizing part 2 is the TPU. We're doing this because we can't make general purpose processors go a lot faster. We picked neural networks, which is useful for a lot of things. It helps with many tasks. A key part is this very large matrix multiply unit, and it's 2-dimensional, which matches neural networking needs. The CPU has about a dozen or so 1D ones, and so does the GPU. It uses 8-bit integers instead of 32-bit floating point numbers, and it drops a bunch of features so it can be a small and low power chip because you don't need those general purpose features if it's domain specific. It has a single thread of performance. One program is running at a time where the other ones have a dozen or so, which makes it hard for that response time limit. It could run the neural networking applications of today. It's flexible enough, it's not hardwired, and TensorFlow let it be at a very high level. All right, that's part 2. Part 3, open instruction set architectures. We've already said RISC is the conventional wisdom of the best instruction set, but how many instruction sets are there on an SoC? About a dozen. Amazingly, there's a dozen different instruction sets for the reasons you see on this slide with separate software stacks. Do we need that? Why do they all have different instruction sets? And they're proprietary. Our colleagues in software have open source operating systems, open source databases. Why don't we have open instruction sets? Could you do that? And that's what I'm going to talk about now. So RISC-V, it's called RISC-V because I was involved with 4 RISC projects at Berkeley, and they kindly decided to name this one RISC-V. So we were doing our research about 8 years ago or so, and we had to pick an instruction set to do our research in. The obvious choices were ARM and Intel, but A, they were too complicated, and B, we were prohibited by law from using them, so we had to do our own. So we started a short project to do our own instruction set. It'd be clean slate, taking advantage of starting 25 years later to do a better design. I was involved. It was led by my colleague Krista Osanovich, and the 2 graduate students that led it were Andrew Waterman and Jens Lee. So it took us a lot longer than a few months to release it, but you know, when you're in academia, industry complains all the time about what you do, about you're not doing a good job of education, so we're used to that. But we started getting complaints along these lines. How come you changed your instruction set from the fall in your courses to the spring in the courses? Why did you do that? And that was an unusual complaint. So when we investigated, why did you care what we did in our courses, which instruction set we used, we found out there's this apparently a need had developed for an open instruction set architecture, and they looked around at what was available and they liked RISC-V, so they started using that. Well, once we realized there was this need for an open architecture, we thought that was a great idea, and kind of following Donald Peterson's tradition, we would try and help industry be successful in using those ideas and make it open. So what's different about RISC-V? First of all, it's really simple instruction set architecture. It's far smaller than the others. So the x86 the manual is like 2,500 pages, and it would take you a month to read it if you read it every day, 8 hours a day. RISC-V is 200 pages. You can read it in an afternoon. It's clean slate. We're no baggage, and we learn from the mistakes of others. It's modular. There's a very small base instruction set that's almost identical to the architecture that was presented here 34 years ago in RISC-V. And it's designed to support domain-specific architectures of extensibility. So there's actually 2 instruction sets designed, a 32-bit and a 64-bit instruction set. The optional extensions include multiply, divide, atomic operations, single and double precision floating point, and a very nice vector architecture. Opcodes are set aside so you can do the domain-specific extensions to it. And it's to keep it, you know, if it's just a university project, it's hard to bet your company on that. So like other open source efforts, we started at Foundations, and it's taking responsibility of the architecture. There's at least 100 members involved. I'd just like to mention 2 of them are NVIDIA, which announced at a workshop that they're going to put them in, there's going to be a RISC core in every NVIDIA GPU chip in the future, so that'll be tens of millions per year. And Western Digital at the last workshop announced they would put a RISC core in every disk that they make, so that'll be billions of RISC cores per year. An interesting way to do this is because it's a minimal instruction set and you have optional extensions, how do we add more extensions? Classically, what happens in architecture is a company announces some new extension and then all the software people in the world complain about how they got it wrong. This time we're doing the complaining up front. We're having groups of individuals and companies get together and proposing it's almost like a standard in advance, like maybe like JEDEC does, and you agree what's the right ideas in an open conversation before you put it in. Andrew and Andrew, the other architect of it, did a book you can get a hold of. So let me go ahead and summarize these slides and it'll take a few minutes to talk from a historical perspective. Like I said, I can't believe that RISC is still the best idea in instruction set architecture, but it is. RISC-V is free and open. That means, what people ask what that means there's no proprietary lock-in. You don't have to, if you join the RISC-V Foundation, you can use it. Anyone can buy it or sell it. It's much simpler, which helps because people want to verify that the instruction set is correct, and security and verification are very important. And so it's popular with security people. The simplicity of the instruction set makes a big difference at the low end in terms of area and power, and it tends to be faster too. As you get a much bigger design, the instruction set plays less of a role, but you can have very fast implementations. It's very easily extensible, which we need for the domain-specific architectures. There's opcode set asides. And a big difference is right now, you think with x86, there's 2 companies that build those, AMD and Intel. And if you don't have one of their badges, you can't design their processors. For ARM, you either work for ARM or there's about a dozen companies who've paid millions of dollars to have the rights to design their own. But there's a small number of organizations that can design ARM processors. With RISC-V, everyone, universities, companies, everybody can design processor architectures, and we're starting to see people putting them into the open source space. So there's Berkeley and universities in, I think, ETH in Switzerland have put out open source versions, which people are just downloading and using and putting on their chips, and they've been used many times. So I think we're going to see a lot faster innovation in this much more competitive environment because it's an open instruction set architecture. And our modest goal is for the project is to be become world dominating, to be the instruction set that you run everywhere. So what I wanted to do is take advantage of my return to ISSCC is to point out just how popular these ideas already are. And here's our talks that are related. The first talk 2.5, is around security. It has our fearless leader, the ISSCC general chair, is one of the co-authors. And they're using a RISC-V processor on that chip for security. Tonight, Norm Juppy. Norm is the architect, the lead architect of the TPU, and he's going to bring both the TPU version 1, which is the one I talked about a little bit, and which is, if you heard the earlier talk, that's for inference, and TPU version 2, which is for training, and he'll be here at what's called this new thing called the Industrial Showcase tonight, and he'll bring hardware with him and talk about it some. And Franz Schistermans, I hope I said that right, he's also giving a presentation, and he's giving a presentation in the this idea of open source hardware. NVIDIA has decided to make their edge inference device, the deep learning accelerator, free to anybody who's going to use it. They have, the sources are going to be available. Franz and I are both on the RISC-V Foundation Board of Directors, and so I know him well. But so that's another exciting thing. That's tonight. And then my colleague from France, who worked in Germany, Olivier Thiemann, who's an early leader in these things, is going to give a talk about devices at the edge. That's 13.1 on Tuesday at 1:30. And then Thursday, the whole day is dedicated to a short course on machine learning. There's 4 sessions there. Okay. The last slide in the conclusion, and wax philosophic here. This ending of Moore's law and Dennard scaling means, performance, energy is going to have to come from innovations in instruction set design, something that's visible to the programmer and the compiler. I think domain-specific architectures and RISC-V are going to play a big role in this change in architecture. And to put the TPU in perspective, this factors of 30 to 15 better is amazing for commercial products. You can think of Intel dominates the server market because its processors or its microprocessor may be 1.5 times better than the AMD, and they dominate the market. Right? These are factors that you don't usually see in between commercial products. So it indicates why people are excited about the domain-specific architectures. I think what we're doing, and reflecting over my career, I think we're entering another renaissance era in computer architecture. In the 1980s, there was a lot of excitement, lots of startups, lots of hardware. It attracted great people to the field. My colleague, just a random example of a great people field, is my colleague John Hennessy. John Hennessy became the president of Stanford, and he was the president of Stanford for 16 years. And not only was he probably the greatest president in Stanford history, he was the greatest college president in the United States during his year. So we were able to attract people like Hennessy to the field. I talked to my colleagues about the incoming PhD class in computer architecture at Berkeley, the people who are applying to get in the fall. It's the best class that they can remember. They couldn't not accept them as many as they could because they were so fantastic. So I think undergraduate students are getting excited about this, what's going on in designing hardware again. And particularly, it might be this neural networking that's part of it, but we're getting great people as input. And then startups, hardware startups. As last month, New York Times talked about 45 startups around the things I was talking about, domain-specific architectures, and 5 companies with $100 million investments and more than $500 million. So these are exciting times. I'd like to thank you all for inviting me here, and I look forward to seeing what you guys do next. Thank you.